Okay, we're working related rate problems, and we want to find the rate of change of the distance between the origin and a moving point on the graph of. And here is the equation here. We're given dx over dt is 1 centimeter per second, so that's pretty slow, I guess. 1 centimeter per second? No, maybe that's kind of fast. I don't know. Maybe it's fast for a slug. Um, Maybe not so fast for a turtle. Let's take a look at the graph. Okay, so this is the part of the graph here. Well, I mean, we could be concerned about the whole thing, but anyway, when dx over dt is 1 centimeter per second, what we're going to want to do here is we want to write a function that is the function of the distance with respect to x, or I guess you would say distance as a function of x. Yeah, I think that's the way they say that. So we need to come up with some kind of relationship between this distance and x right here. So we're going to be using the distance formula. If you're given 2 points in the plane, we can find the distance between those 2 points, and we're going to plug that into the distance formula. Except this particular point here is just going to be general because, right, I've just kind of froze it in time right here. This point could be here, or it could be here, or I guess it could be over here or down here. It could be anywhere on the graph. But I think actually I did a graph and I only graphed it from 0 to 5 or something like that. I don't know. We'll look at that here in a minute. But this is going to be just a general formula. All right. So let's get started. So here is the relationship y and x. This is our relationship up here. Now here's the point at the origin, and then remember this here is just a point on the graph. So this is our x coordinate and our y coordinate right here. So here's our distance formula we're going to be using. This is the difference in x's squared plus the difference in y's squared. Okay, and so we're going to take this 0, put it here, and this x and put it here, and you're finding the difference, and then we square it. Then we do this one here, so 0 goes here, and then the x cubed plus 1 goes here, and then of course whole quantity squared. Now we want to simplify this down, so now we have distance as a function of x here. We have x squared plus x cubed plus 1 quantity squared. Now we're going to take the derivative of this with respect to t. But before we take the derivative, I must mention we need to get this out of radical form, get it into exponential form. So what we're going to be doing, remember to take the derivative. You take the, if we took the derivative of d, we just get 1, then we write dd over dt. And then over here, we're going to take this half, we're going to bring it out front. We're going to subtract 1 from the half. That's going to give us a negative a half. And then we're going to take the derivative of what's inside and chain it out. So we brought the half out front, we rewrote everything in parentheses, subtracted 1 from the half, we get negative a half, and then we take the derivative of the inside, and the derivative of x squared is 2x, the derivative of x cubed plus 1, quantity squared, so we take the 2, we bring it out front, right, rewrite everything in parentheses, and then take the derivative of the inside and chain it out. So the derivative of x cubed is 3x squared, and the derivative of 1 is just 0. But we tacked on a dx over dt. Now you notice I did it out here. I could have done this individually. I could have taken, right, as soon as we took the derivative of x squared, we wrote 2x. I could have wrote dx over dt here, and then we took the derivative of this part here, wrote dx over dt. But then we just have to factor it out. So I just went ahead and just wrote it outside. Now what we're going to do is, well, we need to clean this thing up. It's a mess. And we have a negative a half here, so we'll just go ahead and take that, bring that down into the denominator. Okay, bring that down into the denominator, and now we just keep this up, all this stuff up here in the numerator. And then what we need to do, I guess, is simplify what's going on inside these parentheses here. Let's simplify that. So let me scroll down the screen. Okay, speeding things up. So we simplified it, multiplied everything by a half up here in the top, which looks like I just rewrote it or something. Oh, I reordered the terms, reordered them. Then multiplied a half by everything. And of course, we go ahead and plug our dx over dt in, which is 1 centimeter per second. There's our general equation. You can start plugging x values in and check out what this dd over dt is.